Hello and welcome to today's lecture on MOS transistors. This is the fourth lecture on the low power VLSI circuits and systems course and third lecture on MOS transistors. In the last lecture, we have discussed how the operation of a MOS transistor can be visualized with the help of a very interesting model known as fluid model. And fluid model, as we have seen, can be applied to any charge control devices including MOS transistors. There we have seen how the MOS transistor operates and how the current flow through the channel between the source and drain can be controlled with the help of gate voltage and also the drain voltage. And we have seen that there are three modes of operation. One is the accumulation mode, another is the linear mode, and third one is the saturation mode. And based on that, the characteristic of MOS transistors can be divided into three regions, as we have seen: cutoff region, linear region, linear or active, or that partially charge control device, that means partially deplete, that is actually called when the inversion region is partial, weak inversion region. And then the strong inversion region is represented by saturation region, rather weak strong inversion mode is represented by saturation region. And today I shall discuss the electrical characteristics of MOS transistors. And here is the agenda of today's lecture. After a brief introduction, I shall show once again the structural view of a MOS transistor, and which I shall use to explain the operation and also derive expression for the drain current, and particularly which is known as the electrical characteristics of MOS transistor. Then I shall discuss about some of the important parameters like threshold voltage, and another related subject, related topic is body effect, and we shall see how how the substrate voltage can be changed to change the threshold voltage with the help of body effect. Then another important phenomenon is known as channel length modulation. I shall discuss about that, and finally, I shall discuss about transistor transconductance. So, here is the introduction. As I have already mentioned, the drain current IDS depends on two variable parameters, the gate to source voltage VGS and drain to source voltage. Of course, here I did not mention about another important electrical parameter, that is your body bias, that is your body to drain, body to source voltage, rather source to body voltage. That also affects the operation, and with the help of which the threshold voltage can be controlled. So, essentially three voltages: gate to source voltage, drain to source voltage, and the source to body voltage. These three voltages will control the drain current. And as I have already mentioned, there are three regions of operation: the cutoff region, and this is represented by the accumulation mode, where there is no effective flow of current between the source and drain. And we have already seen in this mode, actually gate voltage is less than the threshold voltage, and there is no channel formation. So, there is no inversion layer. So, there is no channel through which current can flow. So, in this particular region, there is no flow of current, no effective flow of current between the source and drain. Here I am telling effective flow. The reason for that is there is very small amount of current that flows through the device, but for all practical purposes we can neglect it. That is why you are calling it effective flow of current. I mean the no effective flow of current, but very small amount of current flows, as we shall see, that is represented by the subthreshold leakage current. Later on we shall discuss about it in more detail. Then we shall consider the non-saturated region. This is the so called active, linear or weak inversion region, as I have mentioned, and here the drain current is dependent on both the gate voltage and drain voltages. So, as we shall see, the expression for drain current will be dependent on both gate and drain voltages. Then the third region, which is represented by the saturation region, this is the so called strong inversion region, where the drain current is dependent on the drain to source voltage, but does not depend on the here there is a mistake, does not depend on the gate voltage. Sorry, it is independent of the drain to source voltage, but depends on the gate voltage. That means, in the saturation region, the drain current solely depends on the gate voltage. It does not depend as you change the drain voltage, as we shall see. So, these are the three different regions. Now, I have already shown you this structural view in the last lecture, and particularly there are three important physical parameters. I am calling it physical because when you do the fabrication of a MOS transistor, then you will decide the length of the channel, the width of the channel, and thickness of the silicon dioxide. These three are decided at the time of fabrication. So, these physical parameters will affect the operation of a MOS transistor and obviously the electrical characteristics of the MOS transistor. So, we shall express the drain current in terms of these three physical parameters: L, which is the length of the channel, W, the width of the channel, and D, thickness of the silicon dioxide layer. And as you can see, on both sides of this channel, we have got the source, I mean the diffusion regions, heavily diffusion regions, and here also you have got another diffusion region that is called as drain. So, you have got source and drain, and here is the gate. On top of the silicon dioxide, we put polysilicon layer to form the gate, and we can take electrical connections from source, gate and drain to realize circuits. Later on we shall discuss about that. Coming to the electrical characteristics, I shall try to derive the expression for drain current in the same line of the fluid model. We have seen in the fluid model, because of the voltage that we applied at the gate, some charge is induced. So, inversion layer is created, charge of opposite polarity. In case of NMOS transistors, it is the electrons which are created, and that charge can flow, rather current can flow between source and drain whenever you apply some voltage between source and drain. So, charge is, I mean that inversion region is created because of the gate voltage that we apply, and then because of that creation of charge, a conducting path is obtained, which is known as channel between the source and drain, and current will flow. When you apply a voltage, you apply an electric field between the source and drain by applying a voltage to the drain with respect to the source. So, let me write down the drain current expression. So, IDS, drain to source current. So, IDS can be represented as charge induced in the channel, charge induced in the channel, which you can call it IC, rather QC, and that can be divided by the electron transit time. Electron transit time. Transit time is Tn. So, that means here as you can see, not only creation of charge is important or formation of inversion layer is important, it is necessary that the electron will move from source to drain. As you apply a voltage, electron will from one end source end to the drain end, and that will lead to a constant flow of current, and as a consequence this electron transit time is important. So, as you know that Q, that charge that is accumulated in a parallel plate capacitor is equal to C into V, where C is the capacitance, and as we have seen, it can be considered as a parallel plate capacitor, and V is the voltage that is applied across the parallel plate capacitor. And as you know, this capacitance C is equal to epsilon V epsilon A area of the plate and the D thickness of the silicon dioxide layer. So, here epsilon is the permittivity of the insulator, permittivity. Permittivity of the insulator, and this E will be equal to in this case we shall be using silicon dioxide. So, EOX is equal to 3 point roughly approximately 3.9 epsilon 0, where epsilon 0 is the permittivity of the free space, and this we shall use to represent the to find out the expression for the current. Now, this is the expression for capacitance. What about the electron transit time? Tn will dependent on what thing? First of all, it will depend on two things. Number one is speed, and second thing is the distance. So, we can say that transit time Tn will be equal to mu n into E ds. That means, mu n is the mobility of electron. Mobility of electron. Here we are considering NMOS type transistor. So, the charge carrier are electrons, that is why we are considering mobility of electron, and EDS is the drain to source electric field. We shall find out what is the drain to source electric field. EDS, it is dependent on what? It is dependent on the voltage that we apply across the drain to source. So, the EDS will be equal to VDS by length L. So, EDS by L. Now, based on this we can find out the electron transition time. So, electron transition time will be equal to first of all, let us find out the velocity of electron tau n. Tau n is equal to mu n VDS by L, and therefore, T n electron transition time, this is the velocity of electron, and T n will be equal to electron transition time, that will be equal to L by tau n, length by tau n, that will be equal to L square mu n by VDS. So, we have got the expression for the electron transition time, and it has been found that typical value of mu n, that is the mobility of electron, is equal to 650 centimeter square by volt, and that is at room temperature. So, we have got the expression for, we have got the value, the charge that we can obtain by C into V, and we have also found out the electron transition time T. Now, we can find out the current IDS. Now, to do that we shall divide the entire region into three parts, as we have seen. Number one is cutoff region, when the voltage is less than the threshold voltage, there is no channel formation. So, there is no current. So, we are not writing any expression for current for that. Now, we shall write down the expression for the non-saturated region. Non-saturated, or we also call it linear or weak inversion region. In this weak inversion region, we can find out the current. First of all, let us find out the effective voltage that is being applied between the source and drain. As we have seen, we are applying a voltage VDS between the source and drain, on the gate, I mean VDS between the source and drain. Let me draw the diagram here a little, that will make it easier to understand. So, here is your source and here is your drain, this is the channel, then you have got the silicon dioxide and top of that you have polysilicon. So, what you are doing, you are applying a voltage VDS, positive voltage. So, this is your VDS between the source and drain, and you are also applying a voltage VGS between source and gate. This is your source, drain, and this is your gate. So, VGS. Now, although you are applying a voltage VGS between the source and gate, the effective voltage across the channel is not same, because this drain voltage that you are applying is interacting with the voltage that you apply at the gate. So, although you are applying a gate voltage VGS here, the effective voltage in this channel region will be different. For example, in here the voltage, you know that the voltage VDS will be across this length L, and here you can say the voltage is 0 and here the voltage is VDS. So, if you take the average value of 0 and VDS, this will be equal to VDS by 2. Therefore, the effective gate voltage will be equal to VGS that you apply here minus VT, threshold voltage. As we know, you have to subtract that threshold voltage, because you know before that there will be depletion region. You will require a voltage VT, only after that the inversion region starts, and as a consequence the effective gate voltage will be VGS minus VT minus VDS by 2. We have taken the average value. Of course, it will be varying across the channel, but we are taking the average value. This is the effective gate voltage. Now, the current, we can derive the expression for current. Expression for current. For that purpose, first we shall find out the QC. This QC, charge induced in the channel, is equal to C into V. That means, C is equal, the QC is equal to C into V, that is equal to C. What is C? Value of C? Epsilon, this is your oxide into area, that is equal to W into L, because we have seen that parallel plate capacitor has an area W, with W, and L is the length. So, area is equal to W into L by D. This is the capacitance, and your effective voltage will be equal to VGS minus VT minus VDS by 2. So, this is the charge that will be induced in the channel. So, this is the charge, and now we already know the electron transit time. What was the electron transit time that you find out? This is equal to L square by mu VDS. So, this we can substitute, that means IDS is equal to QC by Tn, that is equal to epsilon oxide into W into L by D into VGS minus VT minus VDS by 2, and it will be divided by L square. This is the expression for electron transit time. This is the L square, Tn is equal to L square by mu n dVs. So, what will happen here? You will have L square and mu will be here, mu n will be here in the numerator, it will go to the numerator, and here you will have VDS. So, this is the expression that we get. This is mu n, and this L will cancel with square. So, ultimately we get an expression that is equal to W L, it was L square W L by D. The current expression that we get is equal to W mu n, this is mu n epsilon O x, this is your permittivity of electron, into D into L, and here you get V G S minus V T minus V D S by 2 into V D S. Now, this is the current that flows through the electron. So, that will be the current that will be flowing through the electron. Now, you can express in terms of two other important parameters. One is known as K. K is a constant which depends on the fabrication. So, what is the value of K? K is equal to, we can express it, this current in terms of K, which is equal to mu n, this mu n and epsilon O x by D. You know, when you fabricate, these three parameters are kept usually constant. We usually change the length, this L is changed, width is changed, but these three are usually kept constant. That is why this is sometimes is replaced by K. That means, if we substitute this value of K, we get I d s is equal to K W by L V G S minus V T minus V D S by 2 into V D S. Another, we can also represent it in terms of what is known as the gate capacitance C G. What is the value of C G? C G is equal to this is your E O x into W L by D, that we have already seen, that is the capacitance. This is the, we have already seen, epsilon A by D, here A is equal to W by L. So, we can also express I d s in terms of this capacitance. So, in terms of K constant, in terms of C G. So, I d s we can write as I d s is equal to C G mu n by L square into V G S minus V T minus V D S by 2 into V D S. Okay. So, this is the current that we get whenever the circuit is in the linear region. You may note that we are calling it linear region, but it is not exactly linear. Why it is not exactly linear? Because you can see, if we assume that V D S by 2 is too small compared to V G S minus V T, only then it becomes proportional to V D S. That means, if we neglect this part, only then it becomes linear, and that is the reason why the linear region is not exactly linear, but it approximately linear, particularly when the drain voltage is very close to 0, only then it is linear. So, that means V D S is negligible compared to V G S minus V T, then it is linear. Okay. So, we have derived the expression for the nonlinear region. Now, let us consider the saturated region. So, we can say the second part is your saturated region. So, in the saturated region, what is the key difference between the linear region and saturated region? One important difference is, in the saturated region, the current is independent of the drain voltage, and when it happens, when the voltage drop across the channel is equal to the effective gauge voltage. That means, if the drain voltage is such which is equal to V D S is equal to V G S minus V T, that means, this occurs when V D S is equal to V G S minus V T. This is the effective gate voltage, which is equal to the drain voltage, beyond which, beyond this point, the drain current is independent of V D S. That means, this is the point from where we can consider, we can say that saturated region has started. Below that it is linear or non-saturated region. So, what we can do? We can obtain the expression for drain current in the saturated region by substituting VDS is equal to VGS minus VT. So, we can say that IDS is equal to Kw by L into VGS minus VT minus VGS by 2 into here you can substitute this is ds VDS minus VGS minus VT, we are substituting this VGS minus CT. So, this is equal to Kw by L into VGS minus VT square, and here it becomes, here also it will be VGS minus VT. So, it will be equal to VGS minus VT square by 2. Okay. So, this will be equal to KWL by 2, because half this, if we VGS minus VT square minus VGS minus VT square by 2 will become VGS minus VT square by 2. So, this will be equal to this 2 we have taken here. So, Kw by 2L into VGS minus VT square. So, here indeed we find an expression where it is independent of the drain voltage. So, but it is there is a square law dependence on VGS minus VT. That means, this saturation current will increase at the square law as the gate voltage is increased. So, that is proportional to VGS minus VT square. So, this is the expression for drain current, and also you can express it in terms of the capacitance, that will be equal to Cg mu n by 2 L square into VGS minus VT square. So, this is the expression for that in terms of Cg, gate capacitance, and of course, you can represent it with the help of another parameter. There is another parameter which is known as COX. COX and Cg, these two are different. The COX is the unit gate capacitance, that means capacitance of unit area. So, what is the relationship between Cg and COX? Cg will be equal to COX into W, that area you have to multiply W into L. So, COX into W into L. If we substitute it here, we can write it in this way, this L, it will become L square, this L will cancel out. So, it will be mu n will be there in any case, then W will be there, and it will be COX by 2 into L, and here it will be VGS minus VT square. So, this is in terms of the unit gate capacitance COX. Okay. So, we have seen the expression for saturation current. Now, let us represent the NMOS electrical characteristics. NMOS characteristics. Let us now plot that saturation and non-saturation current. We have seen that we can divide into 3 regions. Let us assume it varies from 1, 2, 3, 4, 5, 1 volt, 2 volt, 3 volt, 4 volt and 5 volt. And this IDS usually varies in the range of in the milliampere region. So, it is milliampere. So, 0 to let us assume it is 0.30 milliampere. So, usually it will vary in this region. Now, as you have seen, there are 3 regions. IDS is equal to 0 for VGS less than VT. We can write VTN if we consider it NMOS transistor. So, which part will represent that this line. That means, this line will correspond to this particular line will correspond to this region. That means, irrespective of the drain voltage, current is 0, IDS is 0. So, this represents the cutoff region, cutoff region. So, this is your cutoff region. Now, nonlinear linear region, IDS is equal to, we have already seen the expression, we can write it kW by L into VGS minus VT minus VDS by 2 into VDS. This part as we have seen is separated by a line. I mean, this corresponds to VDS is equal to VGS minus VT. That means, this part is your linear region. So, obviously, there will be different curves for different gate voltages. So, this corresponds to let us assume VGS is equal to VT plus 0.5 volt. Let us assume this corresponds to VT plus 1 volt, 1.0 volt, and this will correspond to, let us assume this is VT plus 1.5 volt. Okay. So, in this part the current is constant, this part current is constant. So, this is the saturation region. So, this is the linear region, this is the cutoff region, and this is the saturation region, saturated region. And in the saturated region, the current expression is given by, and okay, this is for this non-saturated region is for VGS is greater than equal to VT and VDS is less than VGS minus VT. That means, VDS has to be less than VGS minus VT in this region and VGS has to be greater than VT. So, for these two we call it linear region. This is cutoff, this is your cutoff region, cutoff, this corresponds to cutoff region, this corresponds to linear, non-saturated or weak inversion region, and this corresponds the third region, this is your 1, 2 and 3. IDS is equal to we have seen the expression is kW by 2L into VGS minus VT square, and this happens when VGS is greater than equal to VT and also VDS has to be greater than VGS minus VT. So, this is your saturated region, this corresponds to saturated. So, we have seen, we have derived the expression for drain current for two regions, linear and saturated regions, and we have defined the regions based on the drain voltage and gate voltage. Here we have not taken into account the body voltage with respect to the source. We have assumed that the body is connected to the source. That means, if we consider this diagram, this simple diagram, we can say this body is connected to ground. That means, this is connected to ground, source is connected to ground and body is also connected to ground. And usually this is done by having a region, this is called P plus, and this P plus is actually used to connect the substrate to ground or to some other voltage. Later on we shall see how we can really apply this voltage to have different threshold voltages. So, for the time being let us assume that this drain that source to substrate voltage is 0. Okay. Now, we have considered the NMOS depletion type transistor, we have NMOS enhancement type transistor. Let us now focus on NMOS depletion type transistor. And as we know, in case of NMOS depletion type transistor, a channel formation is done by implanting suitable type impurity in the channel region. So, a conducting layer already exists, and as a result you do not require a gate voltage to form a channel. So, current can flow even when the gate voltage is 0, and you can stop the flow of current by applying a negative gate voltage, and that is precisely shown in this diagram. You can see here, even when the gate voltage is 0, there is a flow of current, and if you want to stop it, you have to apply negative voltage, that is -1, -1 volt, -2 volt and so on. Otherwise, there is no difference in the characteristic curve. I mean, it is very similar to the NMOS depletion type transistor, I mean enhancement type transistor, except that these gate voltages are different for different currents. That means, normally in case of enhancement type transistor, this will start when the gate voltage is slightly more than the threshold voltage, but here as you can see, this is -2 volt. So, in case of depletion mode of transistors, only difference that we will get is the for different gate voltages you will get different curves. That means, you have to apply a negative voltage to stop the flow of current, and if you apply positive gate voltage, then current will increase, and obviously, as we know that it will increase following square law, Vgs minus Vt square. Okay. So, we have seen the characteristic curve for NMOS type transistors, both enhancement type and depletion type. What about the p type transistors? Actually, that can be drawn, say PMOS transistors. We shall not derive expression for that, I shall simply show you the characteristic curve, how it will look like. So, you have got 4 quadrants, you can see here you have got 4 quadrants. This is your IDS and this is your VGS, this is positive and this is negative. For NMOS transistors, the curve is on this side. On the other hand, for PMOS transistors, the curve will be on the negative side. That means, you will be applying the voltage, that drain voltage, sorry, this is your VDS, I have written it wrongly, VDS. So, here it will be negative, here also VDS, but here it is say 0, 1, 2, here it is -1, -2, -3, -4, -5 and so on. That means, you will apply negative negative voltage to the drain with respect to source, and current will flow in the opposite directions, and these are for different gate voltages, and more negative, they correspond to more negative gate voltages. And just like your NMOS transistors, here also there is there are 3 regions, cut off. So, just like your NMOS transistor, here also you have got linear region, this is the saturation region, and this line obviously will represent the cutoff region. This is the cutoff region for PMOS transistor, this is the cutoff region for NMOS transistor. So, on that means, the characteristic curve for PMOS transistor will be on this quadrant, both for enhancement type and depletion type. Okay. Now, let us focus on the threshold voltage. This threshold voltage has been found to be one of the most crucial parameter which controls the operation of a MOS MOS transistor. So, here you can see this corresponds to NMOS enhancement type transistor. You have to apply a threshold voltage I mean VTN to start the flow of current, and characteristic curve will be somewhat like this, that this is the drain current will increase, and as you know this essentially represent the drain current in the saturation mode. That means, in the saturation mode, although I have drawn it linearly, but it will be quadratic, as we have seen this current is proportional to IDS is proportional to VGS minus VT square. So, it increases at this rate. So far as the depletion type transistor is concerned, curve is somewhat similar, but it will be shifted towards the negative quadrant. As you can see, you have to apply a minus VTN, a threshold voltage, which is the minus VTN in this case, to stop the flow of current. And if you increase the I mean negative to less negative to 0 and then positive, then the drain current increases following the same nature of curve, and of course, the amount of current will be dependent on the gate voltage. So, you can see these two essentially represent the drain current with respect to gate to source voltage for enhancement type transistor and for depletion type transistor. Similarly, you can consider the gate to source voltage for PMOS type transistors. This corresponds to the characteristic curve for PMOS type transistor. Here you can see the variation of drain current with respect to the gate to source voltage, and a negative voltage is required for the flow of current, and you can see the curve is somewhat similar, but inverted in this case, because it is in the negative quadrant. Similarly, this curve corresponds to the PMOS depletion type transistor, and here as you can see, you have to apply a positive voltage to stop the flow of current, and as you make it smaller and smaller, and when it becomes 0, this side is the gate to source voltage. So, when it becomes 0, still there is a flow of current, and as you make it more and more negative, the current increases in case of PMOS depletion type transistor. So, these these two and these two represent the variation of drain current with respect to the variation of gate to source voltage, and you can see the threshold voltage actually acts somewhat like the cut-in voltage of bipolar junction transistors. As you know, in case of bipolar junction transistors, flow of current is dependent, it require a cut-in voltage. For example, for silicon, the base voltage should be more than 0.6 or 0.7 volt, that is known as cut-in voltage. Here also it is somewhat similar to that, but we call it threshold voltage, not cut-in voltage. Okay. Now, one very important, as I told, threshold voltage plays a very important role, and on what factors or parameter it depends. You can really derive an expression for threshold voltage in terms of various parameters, but here I have simply taken the expression without, and I am not going to derive it, and as you can see, Vt, the threshold voltage, is equal to Vt0 plus gamma into root 2 phi minus 2 phi plus Vsb, absolute value of that, and minus absolute value of 2 phi v. Here this gamma is known as substrate bias coefficient. Why substrate bias coefficient? As you can see, this Vsb is actually the source to body voltage that you are applying, source to body voltage that you will be applying. That means, if we consider a curve here, you can apply a voltage between the source and body. That means, this particular source and this body, you can apply positive voltage to the body with respect to the source, and that will actually increase the threshold voltage, as we shall see. So, by changing the body bias, substrate body bias, the threshold voltage can be controlled, and in this expression you have got VSB, that is why it is called substrate bias coefficient gamma, and gamma is equal to root 2 q, q is the charge of electron, epsilon Si which is the permittivity of electron, and Na is the carrier concentration in the substrate. So, Na is the carrier concentration of the substrate, and COX is the unit coefficient, unit capacitance of the gate region. So, this is the expression for gamma. So, it will depend on these parameters, and phi v is the Fermi band potential, which is equal to k T by q. K is the Kelvin constant, and T is the temperature in absolute value of temperature, not in degree or Fahrenheit, and this is the absolute value of temperature, and Q is the charge of electron, and Ni is the carrier concentration of the intrinsic silicon. So, intrinsic silicon will have some carrier concentration, this is the Ni, and Na is the carrier concentration of the substrate, as I have already told. So, based on that you can find out the threshold voltage by substituting different parameter values for a particular fabrication technology. Obviously, so far as this part is concerned, Q, epsilon Si, K, these are constants. On the other hand, the COX is the unit gate capacitance, or these carrier concentrations will vary from one process technology to the other process technology, and as a consequence the threshold voltage will be different. Now, let us take up an example. Let us see we can calculate the threshold voltage, and we can see how exactly the threshold voltage varies as you vary the substrate bias. Phi b is equal to, you can substitute different parameter values. This Ni is equal to 1.45 into 10 to the power 10 centimeter, per centimeter cube, and Na is equal to 10 to the power 16. So, 0.26, and actually this k T by q, as you know, is 26 millivolt, that is the k T by q value, and this is the ratio of the Ni by Na. Obviously, the intrinsic silicon has much lower carrier concentration compared to the carrier concentration of this substrate. That means, as you know, substrate is uniformly doped to have more carrier concentration compared to the intrinsic substrate, and phi b value is calculated. See, this is the value of COX, this is phi b is minus 0.35, and COX is equal to epsilon OX by TOX, and this is the value 7.03 into 10 to the power minus 8 farad per centimeter square, and you can substitute the various values to get gamma. Gamma is equal to becomes 0.82. Here the value of the charge of electron, the permittivity of silicon dioxide, Na, these are all substituted, and COX, these are all substituted, and by substituting various values you get Vt is equal to roughly 0.4, assuming that 0.4 is the threshold voltage whenever the body bias is 0. That means, source is connected to the body, and this part is this is the 0.82, this is your gamma into root 0.7 plus VSB, we have to take the absolute value, and minus root 0.7. Now, you can actually vary VSB to get different value of threshold voltage. So, threshold voltage Vt is not constant with respect to the voltage difference between the substrate and the source of the transistor. As you can see, using that expression, how the threshold voltage can change as you change the substrate body bias. So, you can see here, when the substrate bias is 0, as you have seen, the threshold voltage is 0.4 volt, but as you increase the substrate bias, say from say 0 to 1 volt to 2 volt to 3 volt, it can reach say 1.6. So, over a large range 0.4 to 1.6, a large change in the threshold voltage that can take place as you vary the threshold the substrate bias with and threshold voltage will change. And later on we shall use this and see how the threshold voltage can be controlled to reduce what is known as leakage current, because the leakage current is heavily dependent on the threshold voltage. And later on we shall see, instead of this positive bias, we shall usually apply negative body bias to lower to increase this I mean with respect this is called the reverse body bias. We shall do that to increase the threshold voltage such that the leakage current is lowered. That means, larger the threshold voltage, smaller is the leakage current. Smaller the threshold voltage, larger is the leakage current. Later on we shall discuss more about it. Okay. So, this is the body effect. Now, we shall consider another very important parameter, that is your channel length, rather phenomenon, channel length modulation. Here in our expression for drain current, we have assumed that this L is constant, fixed, it does not really change, but in reality you will see that this L is dependent on the drain voltage. However, this dependence is not visible until the channel length is small. That means, it becomes predominant in short channel devices when the channel length is say 0.25 micron, 0.25 micromillimeter. Then this variation is so small that we do not really bother about it, but whenever we are considering say 60 nanometer or say 45 nanometer technology instead of 250 nanometer technology, then this channel length variation becomes visible, or it cannot be neglected any longer. First we shall show you why this variation ought take place. You can see the channel region is not uniform throughout the channel. The reason for that is, here the drain voltage is 0, here the drain voltage is high, and because of the interaction between the gate voltage and drain voltage, the thickness of the channel region is more near the source and it is very narrow near the drain. And as we further increase the drain voltage, what happens at some point of time, the very close to the drain there is no carrier, that means it becomes pinch off. If we increase the drain voltage further, you will find that that pinch off point moves towards source. So, here there is small region where there is no charge carrier. So, essentially channel length is now becoming smaller than the physical length of the device. So, effective channel length is smaller, and this is that is why we call it channel length modulation. Essentially it is dependent on the drain voltage. How do you take into account? We can take into account by substituting L effective, which is equal to L minus delta L. So, N minus delta L is actually, we can represent it by this, we can represent it by this 1 minus, this is the expression where we have substituted effective channel length and we have got this expression, and this variation is proportional to VDS minus VD sat. Essentially when the saturation starts, that is your VGS minus VT, and this is the VDS. So, this change in the channel length is proportional to the drain voltage. When the drain voltage is large, only then this reduction occurs, and this can be represented, this change 1 minus delta L by L can be represented by 1 minus lambda VDS, where lambda is known as channel length modulation coefficient. So, we can now express IDS in terms of this lambda, and it becomes like this: mu n COX by 2 Wn by Ln into Vgs minus Vt square into 1 plus lambda Vds. So, you can see here it is no longer 1, it is here normally it is Vds. So, but it is 1 plus lambda Vds. So, it varies with drain voltage, and this can be depicted pictorially with the help of this diagram. As you can see, in the saturation region, the although I have drawn it in a little exaggerated form, it will not be the slope will not be so high, but you can see the drain current is varying even in the saturation region because of channel length modulation effect, and you can see here it is becoming it is no longer parallel, but it is there is a point where it is touching, and this is how the characteristic can be represented. Okay. Now, another very important parameter that is known as transistor transconductance. For bipolar junction transistors, which is a current control device, it is represented by gain of the transistor beta, the collector current by base current. On the other hand, in case of MOS transistors, it is a voltage control device, and similar parameter is known as transconductance, that means rate of change of drain current by rate of change of gate voltage. So, here we have seen the drain current is controlled by the gate voltage. So, this transconductance is represented by delta IDS, change of drain current by change of gate voltage delta VDS, keeping the drain to source voltage constant. So, that we can derive as we know IDS is equal to QC by TSD. So, delta IDS is equal to delta QC by TSD, and this is the TSD, that expression we have already derived. We are not going into the details of that. So, delta IDS is equal to mu n CGS by L square into VDS into delta VGS, and GM is equal to delta IDS by delta VGS as we have seen, which is equal to Cg into mu n into VDS by L square. And finally, by substituting VDS is equal to VGS minus VT, we get GM is equal to mu n epsilon INS into epsilon 0 W by D into L into VGS minus VT. So, you can see the gain which is represented by transistor transconductance. More the gain, it is better. We can see it is dependent on the mobility of the device, width of the device, thickness of the silicon dioxide, length of the channel, and the effective gate voltage, which is equal to VGS minus VT. So, this is the parameter, and we can how we can increase the value of GM is clear from this expression, which parameter we can really, that means if the width is more current will flow. So, that is why GM will be more. If the thickness is small of the silicon dioxide, gate voltage will have more control, and obviously GM will be large. Similarly, if the length is small, more current will flow. So, GM will be increased. So, okay. So, here we can summarize. We have discussed about 3 regions of the operation of MOS transistor. We have derived the expression of threshold voltage and explained what is known as body effect, and we have also considered channel length modulation phenomenon, and then explained what is known as transistor transconductance. So, with this let us stop here. In the next lecture, we shall discuss how a transistor can be used as a switch. Thank you.